now start the next chapter. It's known as D operator. But when we apply this rule that we are going to learn in this video, basically, uh, if the given differential equation is the second order differential equation with constant coefficient, then we can apply this D operator here. Okay. So the general form of second order differential equation is d2y dx2 plus p1 dy dx plus p2y equals to r of x. Here, this p1 and p2 are constant, and this r of x is it can be constant or any function of x only. Okay, then we can write this differential equation in this form: d square plus pd plus p2y equals to rx. Okay, so let me explain what is d here. Here d is just this operator derivative. Okay, if I write d2, it means that d2 dx2. Okay, so now I think it's okay that if I write dy, it means dy dx, and similarly if I write d2y is same as d2y dx2. Okay, so here if I take y common, so it will be this function. Okay, so in this differential equation, the general solution will be y equals to complementary function and particular integral. I will discuss about this later, about particular integral, but in this video we will learn about complementary function. Okay, so to find complementary function, we have to make the differential equation as a homogeneous equation. Homogeneous equation means this part, this Rx part, we have to take Rx equals to 0. And suppose the solution of this differential equation is y equals to a e to the power mx, where a is constant, m can be any value. Okay, then the auxiliary equation of the given differential equation will be m to the power n plus p1 m to the power n minus 1 plus pn minus 1 m plus pn. So let me explain this method with an example. So suppose for an example, there is a differential equation d2y dx2 plus 2 dy dx plus y equals to 0, because we have to take homogeneous equation. Now if we consider that y equals to a into e to the power mx be the trivial solution of this differential equation, then if we derivative this once, it will be a n e to the power mx. Okay, and the second order derivative will be a n square e to the power mx. Okay, now if we put this value, second order derivative and first order derivative, in this equation simultaneously, so it will be a n square plus 2m plus 1 e to the power mx equals to 0. Here a is constant, this value cannot be 0. Also, e to the power mx cannot be 0. So it is obvious that we can write m square plus 2m plus 1 is equals to 0. So we can, without this calculation, we can directly write if there is any second order derivative, we can write m square here. If there is any first order derivative, we can write m, and if there is 0th order derivative, we have to write 1 here. Okay, so in this way we make this auxiliary equation, and this equation is known as auxiliary equation. There are some rules to find complementary function if the roots of the auxiliary equation are distinct. Okay, then the complementary function will be c1 e to the power m1x plus c2 e to the power m2x up to cn e to the power mn x, where c1, c2, cn are arbitrary constant. And suppose two roots m1 and m2 of the auxiliary equation are equal, so equal to n, then the complementary function will be y equals to c1 plus c2x e to the power mx. Okay, so if there are n common root which is equals to n, then the complementary function will be c1 plus c2x up to c3 x to the power not is x, it will be x to the power n e to the power mx. Okay, so there are two cases of real roots, and suppose for any different differential equation we get complex root. So it is obvious that complex root will be the conjugate of one. So if one root is alpha plus I beta, then the another root will be the conjugate of this root alpha minus I beta. Okay. Then the general solution will be to the power alpha x. This alpha is basically real part of the root into c1 cos beta x into c2 sin beta x. Okay. So in this way, we have to find complementary function. Now it's time to understand this method with some example. Suppose for this example, we want to find the complementary function. For that, we have to make this equation as a homogeneous equation. Okay. So homogeneous equation means we have to take this Rx part equals to 0. Okay. So therefore, the equation will be d2y dx2 plus 2 dy dx plus y equals to 0. Now, if we take y equals to e to the power mx with the initial solution of the equation 1, so therefore, the, the auxiliary equation of 1 will be m square plus 2m plus 1 equals to 0. Okay. So from this equation, we have to calculate the root. So the root of this equation will be m equals to minus 1 minus 1. So real root but real equal root. So therefore, the complementary function or CF, we denote this function as YCF. So it will be C1 plus C2x e to the power minus 1 into x. So it will be e to the power minus x. Okay. And here you have to write that C1, C2s are arbitrary constant. Now pause this video and try to solve this differential equation. Means try to find the complementary function. The given equation is already a homogeneous equation, so don't need to rewrite this equation. Let me take this equation as equation 1. So if we assume that y equals to e power mx is a trivial solution, then the auxiliary equation of 1 is m square minus 3m plus 2 equals to 0. Now you have to find the root of the equation. So therefore, the root of the equation will be 1 and 2. It's real but distinct root. Okay. So therefore, the complementary function will be y CF equals to C1 e to the power x plus C2 e to the power 2x. Okay. Here C1 and C2s are arbitrary constant. Okay. Now I think it's very easy to calculate the complementary function. So you can pause this video and try to solve problem number 3 as well as problem number 4. So similarly, if we consider y equals to e to the power mx is the trivial solution of the given differential equation, then the auxiliary equation, don't write in this form. So properly write auxiliary equation. The auxiliary equation will be m square plus 4 equals to 0. So the roots are plus minus 2i. Okay. So here we get the complex root. So therefore, the complementary function will be e to the power real. Here the real value is 0. So 0x c1 cos beta x. Here the value of beta is 2. So 2x plus c2 sine 2x. Okay. So we can write this directly c1 cos 2x plus c2 sine 2x. Okay. So in this way, we calculate the complementary function. So now again pause the video and try to find the solution of problem number 4. Here the given differential equation is a homogeneous equation. So the auxiliary equation will be m square plus 4m plus 4 equals to 0, because in the place of second order derivative we have to write m square. In the place of first order derivative we have to write m. Okay. So the roots of this equation will be m equals to -2 -2. It's a real root but equal root, not distinct. So we know how to calculate complementary function. So complementary function will be c1 plus c2x into e to the power -2x. Okay. And here you have to write that c1, c2 are arbitrary constant. Okay. But here, this equation, they give this equation with two initial condition. Okay. So try to first understand the initial condition. The first initial condition is y of 0 equals to 1. Okay. So the first initial condition is y of 0 is 1. The meaning of this initial condition is when the value of x equals to 0, then the value of y is equals to 1. Okay. So here we get the solution that y equals to c1 plus c2x into e to the power -2x. Now, if we put x equals to 0 here, then the value of y equals to 1. So since y of 0 equals to 1, so therefore it will be c1 plus c2 into 0 e to the power 0. So from this equation, we can directly conclude that the value of c1 is equals to 1. Okay. Now, let me check the second initial condition. The second one is dy dx equals to 0. So therefore, the solution it will be, since the value of C1 equals to 1, we can write 1 plus C2x e to the power minus 2x. We just put the value of C1 in the complementary function, or it will be the general solution because the given equation is in the form of homogeneous equation. Okay. So if we derivative this equation, it's basically, we can also write dy dx equals to C2 e to the power minus 2x. First we derivative this, then if we derivative this value, it will be minus 2 e to the power minus 2x into the whole function into x. Okay. Now the given condition say that dy dx equals to 0. When x equals to, let me take x equals to 1 or 0. Let me take 0 here. So if we put the value of dy dx equals to 0 and x equals to 0, it will c2 plus minus 2 1 plus c2 into 0. Okay. So we get 0 equals to c2 minus 2. So we can say that the value of c2 equals to 2. Okay. Here we, using this initial condition, we get c1 equals to 0 and c2 equals to 2. So if we put the values of c1, c2 in the main equation, so therefore the general solution will be y equals to c1 is, value of c1 is 1. So 1 plus c2 means it will be not c2, it will be 2 x into e to the power minus 2x. This is our general solution of the given differential equation. So I hope it's clear now how to calculate complementary function. Now it's your job to find that if the roots of the equations are, suppose, plus minus I and 2, then what will be the complementary function? And suppose the root of the differential equations are plus minus I, plus minus 2I, maybe plus minus 3I. What will be the complementary function? Now, let me take this example also. Minus 2 and plus minus I. Then what will be the complementary function?